Welcome everyone, and thanks for joining us this evening for this webinar. My name is Martina Dorigo, and I'm a dairy scientist at AHDB. Tonight, we will be discussing the impact of copper on performance and health of dairy heifers with Dr. James McCaughern from Harper Adams University. In this webinar, James will describe the effects of both under and overfeeding of copper on performance and health of dairy heifers, with some practical recommendations on copper feeding management. This project is part of the research partnership between AHDB and the University of Nottingham. A little housekeeping before we start. The presentation will take around 40 minutes. There will be time for comments and questions at the end, and we will aim to finish up within an hour. You will all stay muted throughout the webinar. If anyone wants to ask a question, please type it into the box on the right-hand side of your screens as shown in this diagram. At the end of the presentation, Professor Liam Sinclair, also from Harper Adams University, will join James to address your questions. If for time reasons we can't answer them all, you will get a reply by email in the next days. Also, tonight's presentation will be recorded and will be available to watch back on the AHDB Dairy YouTube channel or via the follow-up email you will receive. If any of you are Dairy Pro registered, please put your name, date of birth, and farm name, including postcode, into the question box. Finally, we will endeavor to keep this webinar running as smooth as possible, but please bear with us if we encounter any technical difficulties. We will try, of course, to keep this to a minimum. Some information about this evening's presenter. James McCaughern undertook a degree in agricultural technology at Queen's University Belfast before moving to Harper Adams University, where he completed his PhD on copper metabolism in dairy cattle under the supervision of Professor Liam Sinclair. He went on to join Harper Adams University as a lecturer in 2020. His research focuses on cattle production systems and trace element supplementation. For the Q&A part of the webinar, Liam Sinclair will be joining us. Liam is a professor of animal science at Harper Adams University. His research focuses on dairy cows and includes improving the health attributes of milk, increasing forage utilization, improving mineral nutrition, and reducing the environmental impact of dairy cows. So, without further delay, James, it's over to you.
Thank you for the introduction, Martina, and welcome everyone this evening, sorry. Apologies for this rather dry topic, which I'll attempt both figuratively and literally. I'll try to make it as interesting as possible. So copper, and I'll just select, I think I'll go for purple. Okay, can you have too much of a good thing? So copper is an important trace element component within dairy cow diets, and its dietary concentration has implications for dairy cow performance, dairy cow health, and dairy cow welfare. It primarily functions as an enzyme cofactor in over 300 proteins, with examples including the respiratory process, where cytochrome C oxidase acts as a terminal electron acceptor in the respiratory transport chain. And in layman's terms, that really means that copper is responsible for the energy generation in all tissues. Without the generation of energy, simple biological function that we think of in terms of growth rate, in terms of intake, in terms of body condition score, does not exist. And that's why we see such severe implications of copper deficiency upon the animal. An example of another process would be immunity, where the copper-dependent enzyme superoxide dismutase and ceruloplasmin have been shown to act as antioxidants. In spite of all of this biological significance, and indeed the slides that I'm about to show you, I think a very important thing to remember and set out at the start is that copper is still the most common trace element deficiency within ruminants in the UK. And indeed, clinical copper deficiency does present with a whole variety of symptoms, ranging from the characteristic whitening of the coat, where the animal is no longer able to synthesize darker pigmentation, so black hair becomes white hair, and we'll see that in a second, through to the more economically relevant decrease in fertility, reduction in growth rates, and decreased overall performance. Indeed, we really do think of copper, this tiny little element that nobody takes much notice of, as fuel for the animal. And when we take that away, bodily function starts to shut down one by one, with pathological consequences for bone, heart, and immune function. And here we see some examples really of clinical copper deficiency, ranging from our loss of coat color shown in the bottom right, and then up to our dark left here, up to the top left here, through to our characteristic spectacles around the eyes in the top right, and our demonstration of sway back in lambs in the bottom left. This is the extreme of the condition where muscle coordination is lost and there is an inability to stand. And indeed, it's the extreme of the condition that we can observe in cattle as well. So to understand our current problems or issues in terms of deciding how much copper we actually provide to dairy cattle and dairy heifers, we maybe need to understand where we've come from. Copper deficiency tends to result from one main scenario, and that is where a diet or forage or a feed, for that matter, contains high sulfur and molybdenum concentrations. Okay, so that's where sulfur and molybdenum comes in. These combine within the rumen to form thiamolybdates, which lock up copper and prevent its absorption. Sulfur and molybdenum concentrations vary between feed types, within a feed type, and even within the same field. As sulfur and molybdenum concentrations increase, the quantity of copper available to power your animal will subsequently decrease. And this is something that Liam's going to go into much more detail next week whenever he talks about rumen pH and effects upon sulfur and molybdenum. But importantly, that's where we've come from. Okay, so this slide shows the pathway taken by copper within the animal. So we have free copper. Okay, so copper that has not been complexed by thiamolybdate is absorbed in the small intestine and transported to our liver, sort of our diesel tank, our storage organ for the mineral. So it can either be stored here or it can be transported from the liver around the body in the blood. Okay, so over here to our tractor, where it powers growth and it powers reproduction. Alternatively, sort of our overflow tank for the copper within this organ is the bile in the bottom here, and I'll highlight that there now. Okay, so if we have too much copper, we can excrete it and pass it into the small intestine and out of the animal. Okay. As we can see from the next slide, the liver really is, and I always think of it, at least in my head, as a diesel tank for the animal in terms of copper, and we can indeed go in and actually take a sample and measure liver copper concentrations, which you'll see in our future slides to come. We expect deficiency to occur, now this is not an exact science, but we expect deficiency to occur at approximately 19 milligrams of copper per kilogram dry matter. And that's really our blue dashed line at the bottom, so we can see our loss of coat color again in the bottom left. In contrast, whenever we move into our green region, we can see our healthy liver there, our gritty texture, our healthy pinky purpley sort of color. Okay, but we've spoken a lot about deficiency. If we look at concentrations in excess of this 508 milligrams per kilogram dry matter at the top, this picture is a liver from a ewe with excessively high liver copper concentrations, where she was actually demonstrating jaundice. Okay, in this scenario, liver copper concentrations become so excessive that we have a massive hepatic necrosis or liver failure, and as a result, we then have death. And this is really quite a contrast, because as humans, we don't get up in the morning and say, you know, I need to take my copper tablets today, or I need to lay off the copper today. And this is really an evolutionary diversion where ruminants have went one way and we have indeed went the other, where we are designed to absorb large quantities of copper and our liver essentially giggles at it, has a laugh at it. We excrete the excess straight away, so it's very difficult to poison a human with copper. In contrast, because of that sulfur and molybdenum, ruminants are sort of designed like little hoovers, and they go through the landscape, essentially hoovering up the element wherever they go. So at one point in time, grazing through the landscape would have kept this diesel tank imbalance. They'd experienced different types of soils, different types of vegetation, and it would have increased and decreased and generally remained within the green. But the nature of restricting them to a certain area, and that be wherever our farm or location is, if that is predisposed to toxicity or deficiency, that tends to be the rolling issue with time as a result of the soil and the vegetation that we have in that area. Okay, so in this next slide, we show an approximate range and dietary copper textbook recommendations. So you go to your textbook, you look up, and basically you're working from, I have an animal, so if I have my 300 kilogram heifer and she is gaining 0.7 kilograms per day, she will need X amount of copper to synthesize that tissue and maintain simple bodily function, wandering around, running away, etc., etc. So if you look at our textbooks, which are sort of arranged across the top, we can see that whenever we move from, say, ARC 1980 up to NRC 2001, we move from about 11.8 to 12. And the simple reason is that these different books use different sulfur and molybdenum concentrations. When we then move from one class of stock to another, so say we moved from our 300 kilogram heifer in NRC 2001 down to our 650 kilogram cow, because of your higher milk yield, you can see you're then moving from 12 to 15. But really the point of the slide is to show that generally we think recommendations roughly go from about 10 to 15 milligrams per kilogram dry matter within the dairy world, regardless of what source of information that you use. But the question is really, so this is what we think they should get. How does that actually compare to what we have as practice on farm? Okay, and for that we have a previous AHDB funded project that surveyed mineral supplementation, including copper, on 50 herds in central and northern England. And we don't have supplementation to dairy heifers as such, but this is really the best that we can do. So we have a graph here on the right. The blue dashed line at the bottom, remember this is our 10 to 15, so we think they should be down here. Up the side is our dietary copper, so this is a total dietary copper concentration that these animals were getting on that farm, and you can see farm numbers along the bottom. Okay, the blue dashed line is the quantity that we should be feeding, so that's our 10 or 11 right the way up to 15. Okay, and we can see from the green dashed line that 40 of the 50 herds at that point in time were feeding above the industry maximum guideline, which is our green line, which is our 20. Okay, that's potentially 2 times requirements. And indeed, if we go all the way up to our red line, which was the then EU maximum limit of 40 milligrams, we actually have 6 of our 50 farms were feeding above this level. That's potentially 4 times requirements. Okay. So the question is, does that really make any difference to the animal? And we can see from the graph of cull cow data here that it is estimated that 38% of Holstein Friesian cull cows have either toxic or high liver copper concentrations. That's in excess of the 508 boundary that we've already mentioned. And you may ask, why do they even make it to the abattoir if their concentrations are so high? Surely they should be succumbing to toxicity. And the answer probably to that lies around the resistance of the Holstein breed to copper toxicity. In instances where oversupply of the element en masse is observed, only around 2% of the herd actually succumbs to death. But their herd mates generally succumb to symptoms like reduced intakes, reduced milk yields, and a general ill thrift are observed. Okay, and despite all of this evidence, we still seem to be feeding too much, for which there could be many reasons which are quite varied. Are we unsure about the effect of antagonists? So feeding too much is better than feeding too little. Is there the assumption that there are no negative consequences of oversupplementation? And we may see why, as part of our study in a second, why that might actually be the case, why that perception might actually reside in some fact. And there is simply no one keeping track of how much is fed. You have minerals coming in from boluses, you have minerals coming in from parlour concentrate, from TMR, and simply nobody is keeping track of what quantity is coming and where is it coming from, which adds up to these increased concentrations. Okay, which leads us to our current study, or past study just completed. So in order to determine the potential long-term consequences of this oversupplementation, we took 80 heifers from 4 months of age right the way through to week 14 of lactation. They didn't stop there, but that's where we stopped recording them. And that was really from, in terms of months, that was from 4 months of age right the way up to 28, 29 months of age. Okay, so we had 2 treatments, one being the control, which was what we think are those textbook recommendations, certainly north of what should be considered plenty, and that was 15 milligrams per kilogram dry matter. And then we had a high of approximately 30 milligrams per kilogram dry matter. And that was selected to be representative of the mean obtained from the farms that we surveyed at that point in time, okay? In order to monitor liver copper concentrations, so to go in and monitor our diesel tank, see how full it is, we took liver biopsies at 7 months of age. They were a little bit too small at 4 months of age. So 7 months of age, 13.5 months of age, pre-calving, and then again at the very end. So that's our week 14 of lactation. We also monitored performance in terms of our live weights, our body condition scores, and our fertility during the rearing phase. Then during lactation, we monitored performance in terms of intakes, milk yield, milk composition, and ME balance. Okay, so our first graph here, guys, this is just taking us, so we have our heifer age along the bottom. So this is the first part of the study, which is pre-calving. You can see we're going from our 4 months of age right the way up to our 22 months of age. And then we have live weight on the left-hand side here. Okay. We can see, you can see throughout our controls are the same color, which is our little light blue, and our highs are in our dark black color. And you can see that message across the top here, guys, very little divergence in these lines. Feeding more than required had no effect on live weight throughout the rearing period. Okay, so no effect on mean live weight throughout the rearing period. However, if we look at our next slide, which shows our initial measurements, so our initial live weight, final live weight change. We've also got the same for condition score, and then wither height. Wither height, simply the height of the animal measured across the withers. You can see that we did actually have a significant effect upon live weight change, okay, where our animals that were on this high dietary concentration, remember we're thinking here potentially either no effect or else potentially decreased live weight gains as a result of this increased concentration. You can actually see that they actually gained more live weight, okay, about 0.04 kilograms per day, which is of little biological significance over that period, but they still grew faster. Was probably of more emphasis as we also got an effect on condition score, where they actually had a better increase in condition score relative to those on our control treatment. Okay, so not only had we increased live weight gain and increased condition score, whenever we looked at our first fertility measure, okay, which was our first observed estrus, okay, that's essentially whenever they come into puberty, and our live weight at first observed estrus. Not only did they come into puberty sooner, they also came into puberty at a lower live weight, okay, you can see they came in approximately 30 kilograms later. So our picture at this point in time has really been sort of flipped upside down, where we were expecting potentially negative or no consequences of this high dietary copper concentration, but we appear to have only positive. And importantly, everything the farmer sees, everything I see, everything about that animal tells me that it is thriving and this is beneficial. And if I set those two groups of animals side by side, you would automatically go towards those in the high dietary copper concentration. It was just that obvious in terms of what those animals looked like. But, and there always is a but, The picture really begins to change whenever we look at conception rates, guys. So whenever I look at this one, we've got pregnancy rate to first and second service and our serves per conception. So when we look at our control versus our high, you can see almost a 97% conception rate to first and second service versus 75 for our high. And you can see that also translates into serves per conception. The criticism that could be leveled at this is that they were served younger because they were cycling sooner, but we have kept that constant, as you can see along the bottom here. So they were actually the same live weight and the same age whenever they were actually served in this instance. The reasons for this difference in conception rate are unclear, but may result from hepatic copper interfering with hormones generated in the liver, which modulate both fat deposition, which gives our body condition score effects, and also reproductive function. So we're cycling sooner, but less of an ability to conceive. So the question is, what was actually going on in the liver at this point in time? Okay. So this slide shows the liver concentrations within both treatments up to calving. That's absent here, guys. When we get onto that part of the study, that will appear slightly further on. So you can see a picture at each stage relating to each stage they were at. Obviously, this is a little bit younger than 7 months, so it's probably 4-ish months there. But the rest of them aren't far away in terms of that's definitely pre-calving, and that's 13.5 months. The dashed line, our 508 here, represents our toxicity threshold. Okay, so first of all, you can see that our highs, which are in red here, high, had liver copper concentrations throughout the experiment which were above our control animals, and that's generally what would be expected. It was relatively constant. It was about 165, 150 milligrams per kilogram dry matter higher throughout the experiment. Certainly from other experiments we would expect that. However, what was unexpected, however, were these massively high concentrations at 7 months of age, which I can highlight in purple here, way above the toxicity threshold. And this is probably a hangover effect from the pre-study phase. These calves were reared under commercial conditions using typical calf milk replacer and concentrates, which tend to have copper concentrations well in excess of requirements whenever you do try and work them out. And this has really resulted in a mass copper loading of that animal, as we see here. So we're actually up to almost double with our highs at 800 milligrams per kilogram dry matter. Now that's a mean, which means that some of our animals were well in excess of 1,000. You can then see a decline as they come onto our diet. So that's our 15 and our 30, okay, down to 13.5, and then eventually pre-calving, where they've stabilized within the normal range here. Remember, deficiency 19, so nowhere near deficiency. And indeed, these effects were mirrored in our liver. Okay, so this slide shows our liver function enzymes. So this is our liver function enzyme, GLDH, along the side here. These are normal liver enzyme concentrations of GLDH, roughly about 25 to 30 units per liter, and then our heifer age along the bottom. The principle surrounding liver function tests is that when the liver is damaged, the cell basically ruptures or explodes and releases enzymes into the bloodstream that we can then pick up. So the most common example within the human population would be in instances of alcoholism, where you can go in and they'll measure things like your GGT, your AST, your ALT, and increased concentrations of these enzymes denote damage to your liver. The most reliable alternative when it comes to bovines and copper is actually GLDH. And you can see, unsurprisingly, the mass release of GLDH early on in the study, giving us these really high blood GLDH concentrations, reflecting the liver damage, where the red line denotes normality. Okay. So in conclusion, during the rearing phase, although all visual measures of thrift were greater in those fed the high dietary concentration, Fertility in terms of conception rate was compromised. Okay, so moving on to the post-calving phase, this is where they've calved. We've moved them on to our rick area, which you can see in the background here, with our rick bins that we can then monitor intakes, etc. Okay, so we saw, so this is the same slide, guys. I've basically added in here the calving phase. So they've calved. This was just before calving. This was their liver concentrations, and then week 14 of lactation here. Okay, so we saw at this point in time, despite the same treatments, so our treatments haven't changed, an increase in liver copper concentrations for both treatments into the toxic range by week 14 of lactation. This is probably a result of other dietary factors and how they're influencing sulfur and molybdenum, which Liam's going to talk about at length next week in that webinar. So forgive me if I just brush past it tonight. But unsurprisingly, we have, again, we look at GLDH again. So this is our liver function enzymes. We have increased GLDH concentrations coupled with this increase in liver copper by the end of the study. Oops. But what's probably more important is actually our performance. So we move on to the next one. This slide is showing dry matter intake. Okay. So 0 is parturition. So this is calving. And then we have right up to week 14 of lactation. And you can see dry matter intake was unaffected by the dietary copper concentration throughout those 14 weeks. Okay. Where we had no difference in dry matter intake across the duration of the study, we did have differences in body condition score. So if we look at this again, calving, I'll actually mark that out. Calving's about here, so week 0. This is our body condition score. So you can see them coming in. If we remember the results from our previous study, they're coming in with a higher body condition score. Okay, and our highs, because they're coming in with a higher body condition score, actually, if I just do a straight line there versus a straight line here, you can see this greater loss in body condition score for those on our high treatment versus those on our low treatment. So if we look at any of the science around body condition score and milk yield, they've both eaten the same amount, so they've both taken in the same amount of energy. Those on the high dietary treatment had a greater amount of fat to lose and metabolize to generate milk. So in this scenario, we would expect a higher milk yield from those on our high dietary copper concentration. That's not actually what happened. So we move on to this graph. So this is showing our milk yield. You can see along the y-axis versus our study week along the x-axis. Again, 0 denotes the point of calving. Okay, you can actually see a lower milk yield in heifers fed the high dietary copper concentration. So if I just circle that there, okay, so there's our lower milk yield at week 2. So these animals, the high animals, despite having more reserves available to them, had a lower milk, protein and lactose yield at the start of the study compared to those fed the lower dietary copper concentration. That was really centered around week 2. Now, when you take all of those variables, it was only around week 2 in terms of what we could physically measure, but whenever you calculate those through an ME balance equation, it actually lasted throughout the duration of the study. So those on our high dietary copper concentration were in a greater negative ME balance versus those on our low dietary copper concentration. Now, we're not really sure why this happened. There are copper-dependent enzymes within the liver involved in the metabolism of body fat, and so it's possible that increased copper concentrations introduce some sort of efficiency in terms of moving our body fat to our milk yield, but we're not sure. But the important thing is that this inefficiency, if we look at plasma BHB, which is our indicator, one of our indicators of ketosis, did appear to put those on the high concentration under increased metabolic stress. So if you look at our highs, basically a higher BHB denoting a higher higher metabolic stress. You can see those on our high were higher between week 2 and week 14 of lactation. Now, this isn't relevant clinically within the current study due to the maximum BHB concentrations that were really reached, but in some instances where we're talking about very fat cows, this shows the potential of hepatic copper concentration to contribute as an additional risk factor to ketosis indeed. So in terms of our first lactation conclusions, despite there being no difference in dry matter intake and greater mobilization of body fat, milk yield was lower for those on the high copper concentration. So our take-home message: overfeeding of copper is present on most dairy farms. Often this is because copper comes from several sources and nobody really has a summative figure for how much is being fed. The problem is particularly bad in terms of pre-ruminant calves, and that's really a combination of high concentrations in their milk powder and their concentrate combined with the fact that they are pre-ruminants, so the sulfur and molybdenum is not combining within the rumen to lock up that copper and prevent it being absorbed. So they've got this double whammy. They're being fed too much potentially, and then they've also got, because they're essentially a monogastric at that point in time, this massive ability to absorb it, and then they can't excrete it because unfortunately they're a ruminant in that respect. Okay, this has the potential to reduce conception rates and milk yields, all of which have the potential to increase the length of time a heifer takes to pay back her rearing costs on farm. We would recommend you analyze your forage, your concentrates for minerals, and that you would take all sources into account when formulating diets, and also that you have one person responsible. And that's me finished. Christian.
Okay, awesome. So thank you, James. It was a very interesting presentation, lots of information, and actually lots of questions popping up already. While we wait for some more questions to be added, we would like to remind you that next Monday we will run another webinar where Professor Liam Sinclair will cover the second part of this copper research, which will focus on dairy cows, so lactating cows. So if you haven't done it yet, please do proceed and register. Also, if you are Dairy Pro registered, as a reminder, do not forget to put your name, date of birth, and farm name, including postcode, into the question box. Okay, so we will go ahead now and take some time to answer your questions. Okay, let's start with this first question. Are there diseases that prevent copper absorption? If so, are they metabolic diseases?
Well, there's not, I mean, disease can affect absorption of all components within the diet, and it depends on what that actually is. But other things that can affect liver function, such as liver fluke, for example, can also have an impact on copper metabolism. The main things that affect copper absorption are actually other minerals in the diet. And that's what we'll say a little bit more next week when we go in greater depth on that. So sulfur, molybdenum, which James mentioned, but also iron and manganese and zinc can have an effect. But as we'll discuss next week, we've also come across some other dietary factors, particularly rumen pH, that appears to affect how much copper is available. So anything that will impact from a disease point of view in terms of the ability of the animal to absorb any nutrients, so damage as a calf in terms of scours, etc., that can have an influence. But the main factors affecting copper absorption are other minerals within the diet.
Great, thank you. So we move to another question. Could the conception of age, so high copper cows, heifers, be lower due to lower days of age? I think you have explained that, but if you could clarify that, James.
Yeah, so they were, although puberty was essentially younger, we didn't start serving until the same age, and there was no difference in live weight. So that's automatically taken out of the equation. if that makes sense. So they would have been the same. They started to be served at the same live weight and the same age.
And in fact, they may have had an advantage, because that cycling earlier means that they had another 2 or 3 cycles before they were actually served, compared with the control group. So they came on to estrus earlier, came on to reach puberty earlier, but they were served at the same age and the same live weight. So they actually had more cycles before they were served. And despite that, they had lower conception rates.
At a higher body condition score. They had more cycles, they were at the same live weight, and they had a higher body condition score. Everything was in their favor. Nothing was not in their favor.
Okay, so I have a related question to body condition score. If the higher body condition caused lower milk yield, would it work to maintain higher copper levels but manage body condition score better to reduce that impact?
Can you repeat that? Go on ahead, Liam.
Yeah, sure. Shall I repeat the question?
Yeah, for me, Martina, repeat the question. Yeah.
If the higher body condition caused lower milk yield, would it work to maintain higher copper levels but manage body condition score better to reduce that impact?
Because they were fed the same diet throughout the whole of the rearing period, then that increase in body condition score was something inherently from the metabolism that they were doing. We didn't measure dry matter intake until they got into lactation, so we don't know exactly whether that was due to higher intake or whether it was other factors. So this higher copper intake seemed to have a propensity for them to deposit body fat. So it's a kind of metabolic aspect that's happening, and I think a consequence is the higher body condition score. So I'm not sure that controlling body condition score, and I can see where the question's coming from, I don't think controlling body condition score wouldn't negate whatever the underlying metabolic effects were. They are still having an effect, whether that's to do with liver metabolism or to do with other aspects of fat deposition. So I don't think it would have the desired effect of effectively what you'd have to do would be to reduce intake to try and achieve that, and I don't think that would actually get around the problem, but we don't know. It's an interesting question.
Okay, thank you. Another question, how important is copper source?
Certainly we see massive differences in terms of we see differences in copper source. Whenever we take copper oxide versus copper sulfate, and then if you turn that copper oxide into a bolus, copper oxide should have a decreased absorption versus copper sulfate. Whenever you turn that into a copper oxide bolus, there's actually evidence to suggest it becomes similar. Now, from the work Liam will be presenting, I'm of the opinion that this is of potentially decreased importance. I think that the dietary conditions, if you remember back to the slide I had, where you had these vast changes in diet, in hepatic copper concentration. So we went right the way up. Bear in mind, we're feeding the same thing. So we went right the way from 800 all the way down to almost 150, feeding the same dietary copper concentration. I would argue that to a certain extent, the dietary factors behind that are of as equal importance or maybe even more. Now, Liam will come to that next week as to how much absorption you actually get relative to that figure. If you think 15 to 30 is ×2, and then you compare these vast changes in liver copper concentration just as a result of your stage of production, which is then a result of what's going on in your animal. Is it a monogastric or is it a ruminant? Which there's as many factors under the sun affects. That's the problem with early copper supplementation. There's more factors in there than we could ever imagine. When did it get straw? When did it get concentrate? Did you feed it TMR? When did it get water? Versus copper source. I think people get lost in terms of copper, the copper source and the quantity of copper that yes, that is part of the equation, but I think as of next week, you really need to take into consideration the production of that animal and the other factors you've got in there. Sorry if that's a roundabout way of getting there, Martina.
No, that's great. Liam, do you want to add anything to this?
No, we will touch on it again next week. There
Yeah.
are differences between copper sources, but as James indicated, there's actually other dietary factors that are having a greater effect, and the molybdenum and sulfur are one, but other aspects in the diet can also have a large effect as well. Because as James rightly pointed out, that difference between the low and the high copper, that remained throughout the whole study period. The difference remained the same, but how they both moved in terms of where the threshold of being over or under the maximum liver concentration varied a lot more. And it wasn't that the high ones were increasing in terms of their copper concentration within the liver. They were varying as well. So these other dietary factors, which is what we've been investigating as well, why have we got that much variation in terms of the copper levels for both of the supplementary levels?
Thank you. A question related to copper level in grass sample forages. Do copper level vary in grass samples throughout the years? And how much does it cost to do a mineral screen on forage samples?
In terms of how much they vary, how long is a piece of string? You could go out and in terms of fields, now I have heard of people advocating you go out and sample your fields and you supplement according to those values. I could go out and sample a field tomorrow and I'll get a various value of copper, sulfur, and molybdenum. I can do it on Thursday and I can guarantee you it will be very different in terms of a dry matter basis. We also see what adds in there and makes the situation indeed very complicated is things like a wet year and iron contamination. You can just by and I've seen it through testing continually all the time, if you have a simple rain shower and you have some soil contamination that's been churned up by a dairy herd, you'll find iron concentrations well in excess of their potential to actually decrease copper absorption in terms of what we'd ever see in terms of experiments, well above that in terms of they could deplete an animal in goodness knows how short a period of time. That is possible. So the mineral samples on a field basis are not really that reliable, but in terms of a clamp, that W shape across a clamp, you're going to get quite reliable concentrations to work from that way. But bear in mind, the one thing I would say about, if you look at our results, you will see that on diets where you are feeding, high quantities of NDF, so our straw-based TMRs and our grass silage-based diets, within 15 and 30, you're well within the normal region. So practically on farm, you can actually supply quite a quantity of copper, and you would be relatively sure that you're within the safe normal region. It's whenever you get onto those other dietary factors that becomes accuracy becomes more of an issue, I would argue. You may have something to add on that, Liam.
No, I think the grass does vary. We would refer to that as a primary responsive disorder where there is a lack of copper within the diet. Grass can be down to just 3 or 4 milligrams per kilogram dry matter, and it can be another 10 milligrams above that depending on situations. So there are situations, particularly where you have got extensive grazing of replacement heifers, where you may get what we call a primary responsive situation or a primary deficiency. But really the most important factor isn't that of much more of an effect is things such as the sulfur and the molybdenum and other dietary factors, and we refer to that as a secondary effect, so a secondary responsive disorder then, and that's more likely to be the case when you look at samples that go to DI labs and animals that are deficient, it tends to be that secondary one to other interfering factors rather than the primary. But of course, you can have both. You can have a situation where you've got too low a level, and you've also got a very high level of sulfur molybdenum. Now, James has been focusing on dairy replacements, and he showed about 40% of the livers going to abattoirs from dairy cows were either high or toxic. But equally, if we were to look at beef animals, over 50% of those are actually deficient. So you've really, in terms of cattle, got a tremendous difference between the two industries there. You've got the dairy industry that you could argue is killing them by kindness, by over supplementing, often to try and avoid a deficiency. And you often have the situation in the beef industry, which would also, I suppose, overlap with heifers if they were extensively reared, where they may actually be deficient if they're just receiving grazing, if that grass itself is comparatively low in copper, but also there are other antagonists in there. So we would refer to as sulfur molybdenum as antagonists, which could be depleting that as well. So I think the message is, James has been looking at over supplementing, because that's what we find in the dairy industry, particularly animals that are housed and animals that are on a TMR ration. But I wouldn't want to say that that's a problem in cattle, because the beef industry or any system of rearing animals that are more similar to beef, you can still have this deficiency. And remember, copper is the most widely reported mineral deficiency, and it's also the most widely reported mineral toxicity. So it's got this kind of iceberg effect in there, that it's if you can get the copper right, you're likely to get most other minerals right as well, because it's got such a narrow window of being too much in terms of having a negative effect, and James has demonstrated that, but too little in terms of a deficiency. And we're not downplaying that either. There's a lot of animals out there where deficiency is a problem, and I suppose what we're trying to put over is that we need to quantify that of analysing forages as one, but also in terms of animal status, of which the liver is probably our best means of doing that.
Yes, thanks, Liam. This leads us to a few questions related actually to measuring copper levels. One question, I will just group them, so it's probably easier, but one question is, if you measure the copper level in milk, and if it's too low, can you say that the bulk milk, can you say that the copper in the feed is too low? I think this is something that's been done in the Netherlands, and they report that less than 20 micrograms per liter. The lab says it can't be a shortage. And then I have another question: if there is any quick or handheld reader to test copper in live animals, sorry.
If only there were. I think I maybe answered it with that. I think the issue that we have is that when it comes to measuring copper, and this is the issue that we're always going to have, is that it really is a diesel tank. It doesn't like to let everything else down. It will continue to pump out copper in times of famine, and it will absorb it in times of plenty. And that means that virtually all, the easiest way to measure copper status is plasma copper. You simply take a blood sample and you measure the quantity of copper in there. I'm not familiar with the work on milk, but in terms of plasma copper, when the liver runs out, plasma copper concentrations decrease because it simply can't give what it hasn't got. So in theory, I'd assume milk concentrations would also decrease. And Liam may have read more than that than I have, but in theory, that would also decrease. But at that point, you are struggling to keep your animal alive when it is struggling to synthesize those enzymes and divert copper into the animal. That's whenever you're really struggling to keep the animal alive. So plasma copper, taking a simple blood sample, will tell you if you're about to become deficient. What it's not going to tell you is, are you about to enter toxicity? Because at that point in time, the liver will naturally hold it within the normal range right the way up until that animal's dead at your feet. In terms of what we've got there is we've got liver function tests, and those could potentially be used to tell you, you know, are you supplementing too high? The issue with that one that we will have is that the liver simply adapts over time. It's like a boxer that's gone into a ring, and when it takes the first punch and he goes down the first time, he releases a lot of enzymes. If they get up the next day and he takes the same punch, he releases a little bit less. So if you have a cow and she's excessively high for a long period of time, those enzymes will naturally go back to normal. So you end up in this weird scenario within the dairy industry where you could have a cow who's been at toxically high levels for a very long period of time, and her liver enzymes are normal because they've simply settled down. The liver adapts to that. So in terms of trying to work out, the most important thing, one of the important things, and maybe one of the annoying things, is that our differences in fertility, and we had differences in immunity that weren't presented here, but those occurred within the normal range, what we would think were within the normal range, and they were quite large effects. The issue we have is trying to work out reliably without taking a liver sample, which is highly invasive, as to what those may be. Have you anything on that, Liam? I think that's me.
No, I think that covers most of it.
Okay, great. A few more questions here regarding the calves, and in particular, I assume that the higher liver levels in the pre-ruminant heifers is not just down to the copper levels in the CMR and starter feed, but down to the fact that calves have a much higher rate of absorption of copper compared to adult animals.
So yeah, you take a monogast. You're essentially taking a small monogastric versus a ruminant. When you look at that monogastric, it's probably able to absorb about 70% of the copper available to it. Whereas if we take a ruminant, that could be 0.03 to 0.7, which is a factor of 100-fold difference. So that's the issue we will have with copper at that point in time, is that that calf. And we've seen it anecdotally with other projects and GLDH concentrations, because they can absorb copper so well at that point in time, and because their liver's not adapted to pump it back out, they're probably liver damaged maybe within the first few weeks, and that's really a function of their stage of development.
Yeah, and just to add, the EU limit for calves reflects that. The EU limit for calves is 17, or pre-ruminants is 17 milligrams per kilogram dry matter. That's the legal limit. For ruminants, it's 34, and that's to reflect the fact that until that rumen is fully functioning, and we discuss this a little bit more next week, and that's where you get these thiamolybdates that James referred to, that sulfur molybdenum binding the copper. Until that actually is more mature, then you can still have quite high absorption. Somewhere in a functioning adult ruminant, it could be as low as 3%, whereas in a calf it could be as high as 70%. And whilst it's in that transition phase of going from a calf to being a ruminant, then it's somewhere in between. And the difficulty is that if they're getting a creep feed that's more, that's got a high level in, say, 30 milligrams, and that is the case on many farms, then they're going to absorb more as well. And potentially you're going to cause issues in terms of liver damage at that early stage.
Okay, so this leads to this question. Given the very high copper in the calves, should we be looking at reducing copper to the pre-ruminant calf?
Yeah, it's an area that we've got an interest in just now that we're looking at, but potentially yes. I mean, the legal limit is 17, and if you give too high levels, whilst it's still able to absorb more, then yes, the indications that we have from sampling are 4 months of age, and at 4 months of age, you'd hope that it's onto a fully solid diet by that time, and has been for a few months, but it's still got very, very high levels of liver copper, and as James said, at 7 months, of age, they are around about 800 or so. But some of those animals in there were well over 1,000, 1,100. The question is, not the question is really why weren't they dropping down dead more at that point in time? And maybe they are more resilient to those higher levels, but certainly they had very high levels. And that was at 7 months of age. We don't know at 4 months of age because we didn't sample at that point in time. But we would like to, investigate that a bit more and see whether they are actually got high levels or higher levels at 4 months, and what factors are affecting that.
Okay, great. We have time for one last question. And this question is, did you look for differences in the copper status of the calves out of the two groups? And in particular, the question is, can the DEMS status be part of the reason the weanling calves' liver copper were so high?
Yeah, it is something that we considered. We looked at the calves, not in a very structured way, but the calves that came out of the heifers that James reared. We looked at their copper status when they were calves. This is the calves of the heifers. And we didn't do an awful lot because it wasn't part of the research study. We didn't find any major differences in that in terms of live weight, and we didn't find any differences in terms of plasma copper concentrations. But I suppose the interesting point is, what the liver function would be. In other words, the progeny from animals that have been reared on high levels of copper, are they more or less susceptible to different dietary levels, which is a very interesting question. Unfortunately, we weren't able to follow that up to any great extent.
Okay, that's great. Okay, so thank you, James and Liam. This was the last question. We have additional questions we have not answered due to time, so we will get back to you individually by email in the next days. There will be a feedback form on the screen after the webinar and also in the follow-up email, so please take the time to complete the questions as they will help us with future webinars. We have had a great turnout and participation tonight, so a big thanks to all of you for listening. A special thanks goes to Christian Goodall, who works behind the scenes to make sure that everything goes smoothly. And finally, a very special thanks to James and Liam for taking time out of their schedule to be with us this evening. Thank you all and good night.